defining material properties. So first go to 1D consolidation and then go to ground material property. And so as you can see, I made a few adjustments to your model, or excuse me, to your material properties. I made a top clay layer and a bottom clay layer, and I'll get to those in a minute. But first, another thing I want to point out is that I understand that these two correspond to the two embankment layers here. So instead of a more cool-on material property, what you want to do is you want to change it to an embankment type. So just click on the drop-down menu and then just select embankment. So this model type is specifically for embankments that are being used for consolidation projects. As you can see, you only need four material parameters or general parameters. So once that's there, and what I'll do is I'll name this just embankment 1, just for ease of reference. And then just click modify. And as you can see, when you click modify, this shows up in blue, which means the command went through OK. And I'll do the same with this. So the reason I'm changing the model type from more coulomb to embankment is because the analysis will run faster if there's less parameters to take into account. And also the embankment model type is more specific or more sort of suited towards 1D consolidation because it takes the more coulomb model, which is used for finite element analysis, and it just takes out everything that you don't need for your 1D consolidation. So all you're left with are your unit weights, your cohesion, and your friction angle. So that's all you really need as far as material properties for your 1D consolidation, or excuse me, your 1D consolidation analysis. So I'll just name this embankment 2, to simplify it, and I'll click modify. Okay, so now these two are set, and they correspond to these two, I believe. Actually, okay, so it seems this is embankment 1, so let's assign this. Okay, so let's change this to embankment 2, and then this should be embankment 1. Okay. And then this should be bottom clay, so I'll change that as well. Okay, perfect. So now let's go back to our material properties, and we'll review over the clay material properties. So as you can see, I have two material clays, top clay and bottom clay. So I sort of simplified your model. So I merged those two layers into one, and I just made it one bottom clay layer. So the reason I did this is because when I was preparing this training session, I was referring to a tutorial which goes over how to do 1D consolidation using SoilWorks, and I'll give you a copy of that tutorial so you can refer to it later. But just essentially with that tutorial, there were two main clay layers, and I just used those same material properties or the same clay properties. So let's take a look at the first clay layer. So as you can see, the model type is specifically clay. So just keep in mind that clay is used for 1D consolidation, and it has all these additional parameters that you need to take into account. So in addition to just your unit weight, your cohesion, your friction angle, as well as your permeability coefficients, you also have to take into account these parameters, which are very key towards getting an accurate analysis. So you have your SPTM value, very straightforward, but then you have your compression index, your expansion index, pre-consolidation pressure, so there's nothing there for pre-consolidation pressure. But you also have various ratios which specifically apply to 1D consolidation, or excuse me, towards just consolidation in general. So if you have any questions about what exactly these parameters represent, what you can do is you can just pull up the online manual, and then the manual will tell you just sort of the meaning behind each of these parameters. And you can access that manual, like just by pressing F1 on your keyboard when you're in this menu. So what I'll do is I'll press F1 now, and I'll go to the ground material property. So as you can see, here I'm under my clay model type, and what the manual does is it tells me what each of these material properties represents. So under initial parameters, okay, you click on clay, then as you can see, here's what your parameters, very straightforward. But as far as your various consolidation parameters, you have your compression index, your void ratio, compressibility, and then here under compression index, it gives like sort of a more detailed explanation of what it is. So the slope of the normal consolidation line and applied, and the log of vertical effective stress versus void ratio. Same with the expansion index, the average slope of the unloading/reloading curves, pre-consolidation load, over-consolidation ratio, etc. So I won't go through each of these individually, but just keep in mind that the analysis manual is very useful whenever you come across a parameter that maybe you don't understand. Now, as far as I know, these parameters, they can be calculated through lab tests, but more often, or usually what's the case is, these parameters will be available for various soil and clay types, and it's just a matter of sort of accessing them, whether through databases that are available or maybe previous projects in which these parameters were needed. So yeah, just keep in mind that all these parameters need to be accounted for to some degree. Some of them won't apply to your project, so you can just enter 0, but as far as SPTN values and various sort of compression indexes for the compression index and the expansion index, those are parameters that you would need. So just keep that in mind. So I'll close the analysis manual for now, and then just keep in mind that all of these parameters were taken from a sample project in the tutorial, and as I said, I'll send you a copy of that to refer to later. And then also a period for secondary and primary. So what primary consolidation is, it's sort of that first time period that you're analyzing for consolidation. So for this one, the default one that I used was 2.4 years. But then for secondary consolidation, so for a more extended period of time, you can sort of specify how long you want the program to analyze that for. So for a longer period of time, say maybe you're thinking long term, you can put 20 years or maybe even longer than that if that's something that you need to take into account. But just keep in mind that there's primary consolidation, which is sort of that first time period, the shorter time period, and then there's secondary consolidation, which is for sort of long-term planning. Then the strength increase ratio, which is just basically how your clay increases in strength over time. And then these two are key as well. So I'll open up these logarithmic graphs here. So if we open this one here under E log P, as you can see, I have a value for my top clay as well as my bottom clay, and they're both constants, and the scale is kilonewtons per square meter. So just keep in mind that you need to get sort of accurate parameters for these as well. So typically what happens is each clay layer has its own value for this. So you need to possibly look it up. And then also if you have a variable value, what you can do is you can create a chart here. So for example, you can model how it changes with respect to E here. So I won't go into too much detail about this either, but just it's another important thing to keep into mind. And if you want more detail on this, just press F1 on the analysis manual, and then let me just, and this would be a good exercise to sort of show you how the analysis manual works here. So you can just type into the search bar. Let me see if this is the one. Okay, that's not it. Okay, so let me just double check the E log P curve.
That's what's happening in the real life.
Okay, so if you just open up your first option here, if you go to E log P curve, so here's the definitions here. So they have some samples for you, and they also go into more detail what it's about. So it talks about how the void ratio changes, sort of as a function of the stress level. So that's what you're modeling here. So once again, if you have maybe a more detailed sort of parameters available to you, or if you're doing maybe a larger scale project where these would be sort of critical to your project, you can use maybe a more sort of detailed graph such as this. But typically, for smaller scale or more conservative type projects, you can just stick with a constant. That way you don't have to go to the extent of creating a sort of a larger scale graph such as this. And the same applies with the other two. And actually what I'll do is I'll go over those real quick before I go into detail. So there I created my E-log graphs, which is for sort of goes over the void ratios. And then log CV, it's the same thing. So typically you'll have one for each of your soil layers. And as you can see over here, I have a constant for the top clay, and I also have a constant for the bottom clay. And also they can be variable, so you can create a graph according to your needs. So let's go over quickly what the what this log graph means. So if you go over here, okay, so see the value changes with the change in stress level. So what you can do, you can still look over here. So it's the coefficient of consolidation versus vertical stress. So in other words, how your coefficient of consolidation changes as the vertical stress increases. So once again, if you have, if you're expecting that sort of behavior where the sort of, say you're having sort of a function here where it changes with as sort of a what's the word here? As sort of as a function of the coefficient of, or excuse me, as a coefficient of the vertical stress, you would model it here. But once again, for smaller scale or more conservative projects, you can just stick with a constant value, which is what I've done here. And then what you're telling the program is that no matter how the vertical stress changes, the coefficient of consolidation will stay the same. So once again, you use the variable option for sort of more detailed types of analyses, or maybe larger scale projects where you'd expect that kind of behavior, or that kind of behavior to be critical. Okay. So just keep that in mind. I have all of these sort of values available. So it's just a matter of getting them for each clay layer. So just keep in mind that for the embankment, for the top layers, since they won't be consolidating, I mean, they will have a certain amount of displacement, but it will be dependent on how these two layers sort of displace or settle over time. You don't need any type of sort of those parameters for these layers. Whereas with any type of clay layer, especially since it'll be consolidating, you would need to have these types of parameters. So once again, when you're doing these types of projects in your own time, just make sure to pay close attention to these parameters, to understand what each one means, and to get accurate ones for each of your clay layers. And also, this clay layer or this layer here won't be used because I, sort of consolidated these two. In any case, after you have your material properties assigned, your next step would be to assign certain areas or locations where you'd want to analyze the settlement. So in most cases, you'd want maybe several, evenly spaced sort of areas where you'd want to analyze the depth of settlement for each of these embankments. So in order to do that, just go to 1D consolidation and then select settlement calculation position. So if you click on this tab, this input menu will come up and it'll ask you for a start position in the X direction. So let's say I want to, model several calculation positions just along the length of this embankment here. So my start position would be, this point over here. So I'll just put my cursor, over this point. Just pay close attention to how the X value changes. So the X value there is roughly 16 meters. So I'll type in 16 for the start position. So that's where the first position will be located. Now the next thing I would want to do is I'd want to calculate sort of the entire length of this portion of the embankment, or this first embankment. So I'd put my cursor over this point over here, and it's about 45. So roughly there's about 30 meters here, okay? And I want, let's say, I don't know, 6 positions. So 30 divided by 6 is 5. So I'd have 5 positions, and with 6 meters between them. Okay, so I'll just create the positions, and as you can see, they've been created. And actually, it seems that I'm missing one over here. So what I'll do is I'll try this again. So 16, make it 5, and let's. Okay, this should do it. Actually, what I can do is, if you have a position already created, you can create another position over it. So let's say I want to add another sort of point over here, right? So what I do is I just type in 45 for the start position, leave the increment 0, and then leave the number of positions at 1. So as you can see, the sort of charts where all of your positions are. So there's my next position. So later on, when I do the analysis, the program will calculate the settlement for each of these positions. So the reason, that I'm creating all these different settlement positions is, just to show you how to, model those positions. And then also, if you have, various types of loading, say, for example, if you had asymmetric loading, maybe you had loading on this side but no loading on here, obviously the settlement would be different. So you'd want to calculate the settlement on sort of this area here and this area here just to see how they differ. So typically, you'd create different settlement positions to account for differences in loading or, asymmetric geometry. So in other words, any type of those variables will create sort of differences in displacement along the length of your embankment. Okay, so now my next step would be to create some settlement positions over this embankment as well. So in order to do that, I would just select those positions. So my start position, let's say over here at like 47. So that'll be my first start position. And then my last position, let's say I want it, over here at the end. So it's about 65. So 47, let's see. So 65 minus 47 is roughly 18 meters. So what I'll do is I'll do it every 3 meters, and I'll have 6 increments. So that should total about 18. Okay, so there's my various settlement positions. So once I have these settlement positions selected, just click OK. And now the program will be able to recognize those positions later on when you do your analysis. So now my next step would be to model my loading. So just keep in mind that because this is a 1D consolidation analysis, the loading that you created for your finite element model won't translate or won't work for this model. So you'd have to create a separate one. So to do your loading for the 1D consolidation, just go here, and then just go to line load. Okay. So and then if you want to create a distributed load, if you want to make a point load, you just select the point type, and then you'd select LX. So LX is just the distance away from the curve. So for example, if I have this curve selected, this will be my origin, and say I wanted the load right here, sort of maybe in the middle. I'd make it, well, first let's take a look at how long this is. So this is about, like 9 meters long. So let's say I want it about in the middle, so about 4.5 meters. And let's say I wanted the value to be like -20 or -100 kilonewtons. So as you can see, it'll be applied right to the center over here. But let's say, for example, I want a distributed load. So to change that, if you're wondering why is just sort of the, I believe it's a position out of the plane, let's double check. So let's press F1 under line load. As you can see, it says right here Y, so loading distance in the out of plane direction. So for example, if you have a load that's maybe going into or out of, it's sort of going, say for example, it's going into the screen or further down, you can calculate that, or you can apply that using this option here. But anyway, if you want to create a distributed load, just go to uniform line load, and let's name this pressure load. Okay, you select your curve, so select this one, and then LX, you can just leave it at 0. So if you're to put it at 4.5, what you'd be telling the program is that the distributed load would start over here and continue on till the end. But if you leave it at 0, you're telling the program that it starts at the origin, or over here, and it goes across the entire length of the line. So we'll leave it at 0 for now. And I believe your distributed load value is -10 kilonewtons per meter. So we'll put that. Okay, so the reason it's not showing is because the font is in black and it's sort of above there. But I'll apply it. Okay, there you go. So W just means distributed load, and it's just going across the entire length of the surface there. So that'd be how you'd model your loading. So just keep in mind, for any 1D consolidation loads, you'd have to model them using this this function here. But for your finite element models, you'd have to use them using these options here, which I'm sure you're familiar with. So just keep that in mind. Whenever you're doing 1D consolidation analysis, all of your loads would be modeled with this option. Now, some of you are probably wondering what these options are. For example, strength increase zone and change in drain property. Those are just used for when you have where you're implementing drains into your embankment or into your settlement project. So for example, if I were to model maybe a series of drains growing along this area here, you could model those drains just using this option here. Actually, let me go back over here. You'd have to first model your drain types, and I'm not going to model any drains in this project because you didn't really specify them, but just for future reference, if you were to have any sort of drains, or if you were to account for drainage in your settlement analyses, you'd use this option to define your different types of drains. So here, are the drains that are available to you. You also have, I believe, 2 different shapes of drains. And you just enter your parameters over here. And keep in mind that you can create as many drains as you'd like, and you can sort of compare and contrast maybe which drains would work best for your project. In the tutorial that I'll send you, it's actually a sample of a project with different types of drain types, and it'll model maybe 2 or 3 different types of drains in different locations, and it'll show how the settlement varies with each drainage type. But yeah, that's just for future reference. So as far as these other options here, drain property, strength increase zone, change in drain property, those are just used to tell the program where certain drains are located. And then if those drain properties changes, you can obviously use this option. And then as far as strength increase zone, what you can do is you can select what sort of areas are sort of, so for example, when clay consolidates, it strengthens over time. So if you want to model how that clay strengthens, you'd want to specify certain increase zones. So what I'll do is I'll select these 2 layers here because they're both clay, and as they consolidate, they'll strengthen, they'll become more resistant towards pressure. So let's select these. Okay, so now the program recognizes that these 2 clay layers will increase in strength over time. Okay, so now that I have all of this modeled, I should be able to begin with my analysis cases. So go to Analysis, and then go to Analysis Case. Okay. So as you can see, you have your FEM and your construction stage analysis, but I'll delete these for now since we won't be running them, and I'll add a new one. I'll just name this 1D consolidation, and then I'll just go over. So it's very important here to change the analysis method to match the type of analysis you're running. So take down the drop-down menu and select 1D consolidation analysis. Make sure that's there, and then just use all of the layer sets, and we'll use the self-weight. And I'll move this over so you can get a better view. The self-weight and then the pressure load. So transito, I think that applies to your the distributed load that you make for your finite element model. But that won't be in use because it can't apply to this particular analysis. And as far as boundary sets, I don't think you really need to apply any of those. But actually, let me double check. So I'll click OK for now. Click Close. And then as you can see, this load can't be modeled anymore because it's specifically for a finite element models, and since there isn't any meshing, this load's sort of void for now. As far as boundaries, okay, so boundary set, that's part of the strength increase zone. So what I'll need to do is I'll need to go back, go to Modify, and then just move that into the boundaries being used. Just drag and drop that. Okay. And now, before you click OK, just make sure to click on Analysis Control Data just to specify to make sure that everything is, according to your needs. So what I'll do is I'll change the maximum calculation of days to about 2,000. So I'll add 3 more years, roughly, to the length of the analysis. Total load method, I'll select that. And if you're wondering what these mean, actually, let's go to the manual. And as you can see, so this is the consolidation for FEM. Let's see if I can find the consolidation for LEM. Just go to search. and then will be 1D consolidation analysis control. So let's see if we can find that page. Okay, here we go. So, calculation days, that just shows how far you want to extend your analysis. So the sort of absolute limit of your analysis will go to the preset value is 1,000 days, which is roughly 3 years. But for this analysis, I moved it up to about, I think, 6 years by adding an extra 1,000 days. And then also calculation methods, so on and so forth. So this just sort of shows the differences. So the total load method, as manual specifies, it's a time settlement calculation based on the accumulated load of each construction stage. And then the individual load method just shows a time settlement calculation based on the net load or the total load of each construction stage, and the settlement curve is accumulated. So those are sort of various differences here. So all of this just goes over what exactly you're specifying when you're going over your analysis control data. So I won't go, too much into detail later on when you're creating your own, obviously, project models. It's good to refer to this page just to understand exactly what you're specifying. So going back to this, so I'll leave it at the total load method, and I'll check this off. So I don't want to consider the vertical and the horizontal displacement simultaneously. And as far as your water level, you can specify a starting water level, or you can select a water level that you've already defined. So as you can see, you already have sort of 3 water levels specified. So I'll just select this one, water level 00. We'll use that for now. But any other sort of water levels that you define, you can check those or select those to be your initial water levels. And obviously, if this changes, you'd have that under your construction stage analysis data, how the water level changes. But for now, we'll just assume the water level is constant. Okay, so this should be fine, and we'll click OK. So now, select OK. Close it. Now we'll run the analysis. Click Perform Analysis. So as you can see, the analysis time is very fast, much faster than the finite element model because it doesn't have as much to take into account. So about 33 seconds, it's done. And now if you go to the left here, the program just sort of shows your different, okay, perfect. So the program just shows, your different locations in your settlements. So what you can do is you can use, you can go back and forth between your positions just using this, the drop-down menu. Or what you can do is you can just select directly on the lines themselves, and it'll show you. So this blue bar, or this blue line represents, the total loading that's being put on your clay layers here. So as you can see, the loading is constant. But for example, if I were to model maybe a change in the weight, or if I were to do a construction stage analysis where the embankment is slowly being built, obviously this would sort of increase with time. But since these embankments are just there, nothing really changes. All of this is very straightforward. So it's just straight. And this red line here, this sort of goes over your displacement or your settlement. So as you can see, there's immediate settlement, and then it just stays the same throughout. So even though this is a clay layer, because the load isn't sufficient enough to get it to consolidate or settle past its immediate settlement, the line is straight. For example, if I were to do an increasing load, or if the load was large enough to cause the clay to consolidate very slowly over a long period of time, this would be sort of a slight curve going down, such like so. So as I was saying, you can go back and forth between your positions by selecting the lines themselves. And as you can see, because the embankment is lower on this portion, the total load is lower. But if I go over here, the load is much higher, so it's almost double because the embankment height is double as well. And also, it'll tell you how the ground consolidates or settles. So if I want to maybe get numerical values in my spreadsheet, I can just go to the table here, and it'll tell me my immediate settlement. So right away, just within sort of maybe a couple of days, how much total settlement I have. So as you can see, the primary consolidation or the immediate consolidation is about 0.2 meters, and then over time it'll consolidate by another 0.02 meters. So that's telling you that and what happens is that's curve. It seems to be okay. Yeah, it seems to be very straightforward. So as you can see, the consolidation at the beginning is 0.02, and then the consolidation at the end seems to be 0.0214. Oh, excuse me. So it seems like that's the same. Then if you go here, you can double check. So yeah, the total settlement is it stays the same. So it's very linear, very straight. And these are all your values here. So that's how you would get sort of your settlement or your displacement over several locations. So that's essentially, once again, you can get your curves. And I'm just double checking to see if there's any changes, but it appears that all the settlement in your in this particular project is sort of immediate. So after immediate settlement, what the program is telling you is that there won't be any other settlement afterwards. So even maybe a couple of years after the after immediate settlement, if none of these conditions changes, then the settlement or the displacement will be the same. But let's say, for example, and I have a tutorial here, which I'll give you a copy of. Let's say, for example, you have, and these are just screenshots for the completed project. Let's say you have a project with maybe some consolidation, which isn't maybe it's so linear. So as you can see, for this particular project, there is a certain amount of consolidation. So here it'll give you your primary consolidation or your immediate settlement, and then over a period of time, so this was also 2,000 days, so maybe 6 years later, the total settlement will maybe be doubled, so about by 1.48. So once I send you the tutorial, I'll send you a copy of the completed model file as well. So maybe you can compare and contrast it with your current project. So just keep in mind that one of the main advantages of the 1D consolidation method is that you can analyze how your embankment or how your project site settles over a much longer period of time. So in addition to the immediate settlement, you'll also have a secondary settlement, which shows maybe over a number of years or months the additional settlement that will take place. And that's just the reason I think this one has more secondary consolidation is because I think maybe there's a certain amount of loading on the embankment. I can't really remember, but just go back and double check, and I'm sure you'll be able to see how the way this project was modeled sort of allowed for a curve or a secondary settlement such as this. Okay. So that's essentially, how you do the 1D consolidation with SoilWorks. It's very straightforward. I'd say the main sort of part that's maybe the most rigorous would actually be just doing the ground material properties for your clay layers. So as you can see, all these parameters really need to be accounted for in order to get an accurate analysis. So just make sure that you come ready, that you understand what all these parameters mean, and that you come ready to input that data before you create your model. So that's sort of the main, this is sort of the key point here as far as consolidation analysis. Everything else is, very straightforward and very easy. And as far as, modeling drainage types, that's all included, or is the detailed steps of that are included in this tutorial. You can review that on your own, but if you have questions about it, feel free to contact me. So that about wraps it up for this session. Once again, the focus for this session was just using the 1D consolidation method. I know Edgar, he said that he would be giving you guys the demonstration of how to use the dynamic module, so you can look forward to that. But are there any sort of questions that you have for me at this point?
We have no question from this part.
Okay, I understand. Perfect. So what I'll do is I'll send you just a copy of this model file, as well as the tutorial that I used as sort of a reference. You can try it out on your own. And if you have any questions when you're doing the modeling, feel free to contact me. Just send me an email or give me a phone call, and I'll get back to you, okay?
Okay, very good.
Okay, perfect. Thank you very much for your time. I hope you have a good day, and we'll be in touch, all right?
Okay, right.
Okay,
Thank
goodbye.
you.
All right, thank you. Bye-bye.
Thank you. Bye-bye.